Hi everyone, so today I'm going to be going over an example of Green's theorem, and I'm specifically going to be doing problem number 4 from section 4 of chapter 15 from our textbook. And the problem here is find the line integral sine x cosine y dx plus xy plus cosine x sine y dy over our path C, where C is the boundary of the region lying between the graphs y equals x and y equals a square root of x. So before I go about solving this problem, the first thing I want to do is draw a graph. I definitely find that drawing graphs helps me figure out these kinds of problems much more easily, and sometimes Professor Seeberger requires it of us. And sometimes it might just be easier, at least for me it is. So first I'm going to draw my x and y axes. I'm not going to make it too big. I don't want to take up the whole paper here. But because I already kind of have an idea of what these graphs are going to look like, these are pretty common, I'm just going to draw my axes as such. I'm going to label this y and label this x. It's going to be this origin right here. I'll make 1 right there, and 2, I'm going to spread these out quite a bit just because, again, I kind of already have an idea of what this region is going to look like. But to show you, for those who may not know, so first we're going to start off with y equals x, and I'm sure everyone knows what that looks like. So, of course, 1, 1, and 2, 2. Not very good at drawing straight lines here, so I'll try my best. All right, and that just keeps extending, and I'm going to label that y equals x. It's going to be very important to label our limits of integration, especially when we're graphing them, so we know, or we can use them to figure out how to find the double integral. All right, so now we have y equals x. Now we're going to make y equals the square root of x. So I've actually drawn this in a previous exercise. I think it was for a homework, so I remember what it looks like. And so I'm going to start here. It starts at 0, 0, and it goes up a little bit, and then right where it's going to cross y equals x, and I think it goes on. But in this case, we only need to draw up to where it's going to meet the y equals x line right here. So I'm just going to label that 1, 1, so I know that that's where that meets. And so, of course, our region right here, I'm just going to shade it, so again we know what our region is exactly. All right, so now we have our nice little graph here. We got our y equals x. Oh, and I almost forgot. Let me put an arrow on that, and I'm going to label that y equals the square root of x. And I find something also, again, pretty helpful when making these double integrals is kind of rewriting these. So right here it's given to us as y equals x. I'm just going to say or x equals y. It's the same thing. In this case, y equals the square root of x is also just x equals y squared. And that will be helpful for later. So now to find the integral, we're given a formula here for Green's theorem. I'm just going to write the general formula here. So we have the integral again over our path C, and then it's m dx plus n dy. And then that's also equivalent to the double integral over our region R, and this is our region right here that we graphed out. So I'm just going to put parentheses, so it's the partial derivative of n, not m. I know that can be confusing because n comes first. And something I find a little bit helpful is if you take out the s in Green's theorem, you just have Green theorem. Green, the n is at the end of Green, that comes first, and then theorem. M is at the end of theorem, and that comes next. So I think, it's a little dumb, but it helps me personally to remember that it's the partial derivative of n that comes first. So it's the partial derivative of n with respect to x. My signs kind of look like 2's here. And then it's the partial derivative of m with respect to y. I'm going to close the parentheses, and it's dA here, which is basically equivalent to dx dy. All right, so this is our general theorem here, or not theorem. This is our general formula here for Green's theorem. And now I'm going to go ahead and find our m and n. So if we look here, m dx, let's look up here. We got sine x cosine y dx. So this is going to be our m, our sine x cosine y. I'm just going to write y equals sine x cosine y, just to make it very easy to determine what's our m value here. And then n, so on the other side here, I'm going to write n. We look again, I'll bring you in a little bit closer. xy plus cosine x sine y dy, and we know it's m again because it's next to our dy. So, all right, so it's xy plus cosine x sine y. All right, now we have our m and our n, and now in order to find our double integral, we have to find the partial derivatives. So first I'm going to find, because I've written it down first over here, I'm going to find the partial derivative of the partial derivative of m with respect to y. So I'm just going to write partial derivative of m with respect to y. All right, and for those who might have forgotten, it's with respect to y, so the derivative of cosine is negative sine, so just going to be negative sine y, and we of course ignore the x there, so we just keep the sine x. Now moving over to n, we're going to do the partial derivative of n with respect to x. And again here, because it's respect to x, we're ignoring the y. So it's just going to be y, and then again here we're looking at cosine x. Again, the derivative of cosine is negative sine, so it's just going to be minus sine x, and then ignoring the y, sine y. All right. So now, plugging these into our formula here, I'm not going to write down the limits of integration just yet. I will in 1 second. I just want to write this down here and plug it into our formula. So it's first the partial derivative of n with respect to x. So I'm going to write y minus sine x sine y. I think I'm going to close my parentheses. And then minus, it's not a plus, remember, it's a minus the partial derivative of m with respect to y. So we have, it's a negative sine y sine x. All right, and then again, dx dy, so don't forget that. All right, so we have the start of our double integral here. We just have to finish it off. All right. So now I'm going to look at the graph that I've drew right here, and I'm going to find the limits of integration. So remember, we have dx in the inner side here, so we're going to find the limits of integration of x on our inner integral right here, and then the y is on the outer part, so I'm going to find the limits of integration of y in this outer integral right here. So first, looking at our graph, if we go across the x-axis, we start here at this graph right here, y equals the square root of x, or also x equals y squared. And then as we move across the x-axis, we end up right here, where x is equal to y, or y is equal to x. So we know we're going to start here, and again, it's the limits of integration of x, so we want to write it in terms of what x is equal to. So we start with y squared, because this is our graph y squared, and we end up right here where x is equal to y. So we're going to write y, the top right there. Now for the x or the y-axis, we're going to start here, y is equal to 0, and we go up again where this graph meets the other graph, and it's right about 1, 1. I already have written it right here. So from 0 to 1 on our y-axis. So I'm just going to write 0 on the bottom here and 1 there. And then I'm just going to rewrite our integral. Actually, I noticed something immediately. So we have negative or minus sine x sine y, and then minus negative, which is the same as plus sine y sine x. So we get to cancel those. So I'm just going to completely cross those off. and then just rewrite it down here. So right now all we have is y and then dx dy. So y dx dy. All right, that simplified very nicely. So now I'm going to go ahead and try to solve. All right, I got cut off there at the end, but I was just starting to evaluate our double integral here. And so I have it written as y dx dy, and then our limits of x, we start at y squared and we go to y. And then with respect, or our limits of integration of y, we start at 0 and go to 1. So right now I'm just looking strictly at our y dx, this inner portion right here. So of course, the integral of y with respect to x is just yx. And again, it's from y squared to y. I'm just going to write y squared to y. And then don't forget our dy, because we still have to integrate one more time after this. All right, and this is a nice and easy one. So I'm just going to rewrite it over here as this. All right, and then remember, we're keeping our y. And so from x from y, or y squared to y, that's just y minus y squared, and dy again, don't forget that there. All right, and now if we go ahead and distribute this, I'm going to rewrite it again. We distribute the y, we get y squared minus y3, put parentheses over there, dy. All right, this is, again, a pretty nice and easy integral. So, of course, you know, the integral of y squared is just y3 over 3. And the integral of y3 is just y4 over 4. It's from 0 to 1 again. And in this case, because we have a 0 at the bottom, and there are no other terms really that we need to take into consideration, we can kind of just ignore that. So we just have 1, you know, 1 to the any power is just 1 over 3, and then, losing my grip here, 1 over 3 minus 1 over 4. And again, that's equivalent to 4 over 12 minus 3 over 12. And then I'm running out of room. I'm just going to write this over here. We all know that's 1 over 12. And we don't know specifically what our units are, but as Professor Seeberger has kind of shown us, we can just write units of work. And I'll circle that here. All right, so that is our answer. And this was our process over here. So I want to thank everyone for watching, and I hope this was helpful for anyone who did. Thank you.